Welcome to another exciting episode of Advanced Level Chemistry here at Spain Park. Today is Friday, November the 15th, 2024. Today we're going to finish up our discussion of quantum numbers and relate that to electron configurations and hopefully start tying this up into a big bow so we can be ready to get tested on it sometime next week. Okay, that date is still to be determined. All right, so Jack, what are they supposed to do if they're liking these videos?
Smash that subscribe button, hit that like button, and don't forget to ring that notification bell.
There you go. Now you know what to do.
Don't
All right.
give
So,
him too many likes though. We don't want all the attention going to his head.
so we are talking. Now look, we are talking about quantum numbers. I believe that we got all the way. Did we start talking about the magnetic quantum number, the third one? Did we get to that at all? Okay. Seriously, I need to know. Did we?
We started at
F? Okay, now look, so here we go. So we have, when n equals 1, L can only equal 0. Now I'm going to talk to you about where this m sub L is going to come from. That's our third quantum number, so we'll do that. But on the first energy level, you only have one possible answer for L, and that's our S sublevel. N equals 2, L can equal 0 and 1. It can always equal from 0 up to n minus 1. Again, this is the whole idea that this is the energy that the electron can have. You can't let these numbers equal anything because the energy levels have to be quantized. There's only specific energies, and Schrodinger figured that out in his equations. He limited the energy. That's why we have to limit what the answers can be in order to be able to explain the observations that we see. So L can only equal 0 and 1, meaning we have an S and a P sublevel on the second energy level. On the third energy level, L can equal 0, 1, and 2. 0 always corresponds to the S, the P, and the D. And remember, the S, P, D, and F comes from when the spectroscopist looks at this, they see different characteristic lines. So when an electron transitions out of these different sublevels, they give different types and different characteristic lines, and that's where the SPDF, sharp, principal, diffuse, and fundamental, comes from. It's not just random letters that they put out there. It's just what type of line are they giving off when they transition out of those energy levels. So we have these, every energy level gets a new sublevel. Now, theoretically, when we went to n equals 5, L could equal 0, 1, 2, 3, or 4. Now, n equals 4 there's not really a sublevel that corresponds to that. They say that theoretically it's a G, but by the time an electron had enough energy to get to that sublevel, it actually has enough energy to completely escape from the atom and make an ion. And so mathematically it's possible, but practically or theoretically, or in reality, it never happens because it's never an occupied sublevel. So they don't have a name for it because it's kind of like in Beauty and the Beast, the forbidden wing. It's there, but you're not allowed to go to it ever. The electrons, by the time they could ever go to that sublevel, they have so much energy they just leave. They don't. So F is as high as we could go, although mathematically you can go to G, H, and I. All right. So the third quantum number, just real quickly, we've really already talked about it. It's just justification for how we know that there's 1, 3, 5, and 7 orbitals on each sublevel. So it's called the magnetic quantum number. Magnetic quantum number. And we just use m sub L. And we use m sub L because it's dependent upon the value of L. M is dependent upon the value of L. It can only equal, m sub L can equal from minus L up to plus L. Again, we have to limit how much energy it has. So, if L equals 0, m sub L can only equal 0. Okay? Which means that on the S sublevel, there's only one answer. One answer for m sub L equals 1 orbital. Now what does that mean? Well, on the S sublevel, it's a spherically shaped. Well, there's only, no matter how you orient this, there's only one orientation in space for a sphere. You can't change any kind of orientation. There's only one possible way to have a sphere in 3 dimensions, that's as a sphere. So there's only one possible orientation, one orbital on the S sublevel. But when L equals 1, M sub L can equal -1, 0, and +1. How many answers is that? 3. Well, we already know, we've already talked about it, that on the P sublevel, there are 3 P orbitals. See how they're very directional. Henry, put that away. They're very directional, very axial. Okay? So we have the X, we have the Y, and we have the Z. So there's 3 different equivalent orientations in space for when an electron is in a P sublevel, the path it's taking, there's 3 different possible axes it could be on. All 3 of these are perfectly equivalent in energy. What's the word for equivalent energy? Degenerate. These are degenerate orbitals. Equal in energy. The only thing that's different is their orientation in space. So if you put into Schrodinger's equation n equals 2, L equals 1, and M sub L equals -1, and you do all the math, and you do the probability, and you do that little dot thing that I showed you how they get the shapes, it would come out to one of these 3. Let's just say it came out to this one. So when n equals 2 and L equals 1 and M sub L equals -1, that means the electron with that much energy is most probably going to be found in a place somewhere doing a standing wave pattern, a complex pattern in an area around the nucleus like this. And if it was M sub L equals 0, it would be on this axis. M sub L equals +1, it's going to be on this axis. Okay? So it's just 3 different orientations possible in space. Well, how many d orbitals are possible? On any sublevel, what did we say? How many d orbitals are possible? 5. Well, when n equals 3, remember it can always go up to 0 up to n minus 1. So n equals 3, we can have 0, 1, and 2. So we can have a d sublevel. Well, when L equals 2, M sub L is going to equal -2, -1, 0, 1, and 2. How many answers is that? 5. Each one of these corresponds to the different orientation in space of the 5 d orbitals. They're all degenerate. They're all equal energy. They're just different orientations in space. So in talking about the S, the P, the D, and the F, I already told you there's 1, 3, 5, and 7. But it's the M sub L value that mathematically tells us why there's 1, 3, 5, and 7. So when we get to L equals 3, the F, -3, -2, -1, 0, 1, 2, and 3, how many answers is that? 7. Okay, 7. Therefore, there's 7 possible F orbitals. Super complex in shape, but 7 F orbitals possible. So we have all of these tell us all these things. Now our 4th and final quantum number is called the spin quantum number. And it's going to be M sub S for spin. Now this one's super easy. It's just +1/2 or -1/2. Now, the 1/2 means nothing. It's the sign. And we're going to define it in just a second, but the Pauli exclusion principle says that, and we've already kind of talked about how many electrons can go into any orbital. 2. Okay, so this is, but Pauli found that they have to have opposite spins, like the Earth is spinning on its axis. One's clockwise, one's counterclockwise. When a charged particle spins, it generates a magnetic field. If they spin in opposite directions, they're going to be generating opposite magnetic fields. So the 2 negative things can occupy the same space if they have the opposite spin. Because they kind of make opposite north and south pole type magnetic type things. It's a little bit more complicated than that, but it kind of gets you the idea. So they have to have opposite spins. Now, he won a Nobel Prize for that. Heisenberg won a Nobel Prize for the uncertainty principle. Einstein won a Nobel Prize explaining the nature of light and this whole photon thing and how we figured this all out anyway. So a lot of really smart guys had to do a lot of really incredible things to figure all this stuff out. So it's okay that you're a little like, huh? Okay, because I mean it's pretty complex. Okay, and I'm going to work at trying to boil it down into the basics. And you're based on what other people have said, you learned some of the actual practicality in 8th grade with the whole 1s2 and 2s2 type stuff that we're about to get to. So we have a model now. We have our energy levels N, our sublevels S, P, D, and F. We have how many orbitals can be on this. So it's like, again, that hotel. Which floor am I going to be on? Which hallway in the floor am I going to be on? Which room in that hallway am I going to be in? And what's the maximum capacity of that room? What energy level is the electron in or on? Is it on the first, the second, the third, the fourth? And then, once I know what energy level it's on, I can know which sublevel it's on, which like hallway in our hotel. Which sublevel is it going to be in? Each sublevel can have a variety of different orbitals, different rooms like our hotel, different numbers of rooms. Which room, which orbital is that electron going to be in? And the maximum number of electrons that can be in that orbital is 2, and it has to have opposite spins. Because in nature, opposites attract. And only opposites would go into a room together. Okay, if they're married. Now, little subtleties there. So we end up having these quantum numbers describing where the electron is around the nucleus. Okay? But this is complicated. So when I try to draw it out, we have our 1s with 2 electrons buzzing around. That's all there is. And then so we have this. Then we have our 2s, which is a bigger sphere encompassing that, with 2 electrons buzzing around in it. But on the second energy level, we can also have our p orbitals with 2 electrons in each one of those. Then we go to the third energy level, even bigger, encompassing all that. But notice there's always a gap in between, a nodal region where there are no electrons. This space, and then this space, and then this space. Okay? Then our bigger p, and then technically I have to draw in all the d's onto here too, but I'm not that good. I can't draw the d's. Okay? Holly, follow me. Okay, so when we're looking at all of this, okay, we have to then just say, well, it looks like there's just electrons everywhere. But the reality is they're all following this standing wave pattern based upon their energy. They're actually in different places around the nucleus. But that's complicated. We want to kind of simplify this and get something that's a little bit easier for us to be able to understand. So we're going to go with increasing energy right here. And I want to clarify and say the lower the energy, that simply means the more tightly the electron's held to the nucleus. The higher the energy, the less tightly the electron is held to the nucleus. Okay, so it's not necessarily talking about distance, it's talking about how tightly held is the electron to the nucleus. All right, so stay with me. It's going to get darker before the dawn, but then we're going to come out and we're going to see the light on the other end. So on our first energy level, how many sublevels can I have? 1, right? And on that sublevel, how many orbitals can I have? How many on the S?
1.
I only have 1. So I'm going to draw one line to represent my 1 orbital on the first energy level, on the 1s. Now my first energy level is filled. So then I have to go to the second energy level. On the second energy level, how many sublevels can I have? 2. An S and a P. And on the S sublevel, how many orbitals do I have?
3.
On the S sublevel, how many orbitals do I have? 1. So again, I'm just going to draw one line. But on the P sublevel, how many orbitals do I have? 3. Now, in your notes, it says that the P sublevel, the electrons have a little bit more energy than on the S sublevel. So I'm going to bump them up here and say 2P, a little bit higher on the energy level. But you say, Mr. Hobbs, It's on the second energy level. Why don't they all have the same energy? I'm so glad you asked. I'll find it here in a second. Okay, come on, guys. Come on. Henry, keep that in your pocket. If I look at this graph, this is talking about on the third energy level, the relationship between an S, a P, and a D. Electrons in an S, a P, or a D sublevel. Now again, remember, this is all based on math. This is all based on the probability of where the electron could be found. That's what an orbital is, the most probable place to find an electron. Well, you can see that on the third energy level, that the electrons are all about the same. Here's the nucleus over here. However, 3s doesn't stay out here all the time. There's two little humps right in here, which tell me that there's a small but significant amount of time that the s electron gets closer to the nucleus. Now, when it's closer to the nucleus, is it going to be more strongly held or less strongly held? More strongly held. Lower energy. Okay, our energy scale is measuring how tightly held it is. So the P's has one time it's closer to the nucleus. The D's don't have any. They're really just kind of one little thing here. So on any energy level, because the S's come this closer to the nucleus, a small but significant amount of time, it's actually always held more tightly, a little bit lower energy than the P's. And then the P's are held a little bit more tightly than the D's because of the path, that standing wave pattern that they take, and how close they get to the nucleus. Okay, stay with me. You're turning around, you're doing everything else, everybody's looking at you. You need to stay focused. Okay? Stay focused. So it's all a matter of the path that it's taking and how tightly held it is. On any given energy level, the S's are always held more tightly than the P's. The P's are held more tightly than the D's. Even though the majority of the time they're the same distance, it's this small but significant amount of time it gets closer that makes the difference. That's why we have sublevels. Because they have different paths that the electrons take as the electron cloud gets bigger. The different standing wave pattern. Okay? So that's the explanation for sublevels. So again, how many electrons can go, Jack, stay with me. How many electrons can go in the S sublevel? Two electrons. So on the first energy level, how many electrons can we have total? Two. On the second energy level, how many electrons can we have total? 2, 4, 6, 8. 2 in each orbital. Then I go to the third energy level. On the third energy level, I can have S, P, and D sublevels. So I have the S, I have my 3 P's, a little bit higher in energy than the S. And what about the D's? 5, but in terms of energy, even a little bit higher energy than the P's. So we're going to go up here. 1, 2, 3, 4, 5. 3D. Okay? So this is called an arrow diagram. Leave yourself some space. We're going to keep building. I already don't have enough space. So if I want to look at, let's just say we want to say, how are phosphoruses, 15 electrons, oh, phosphorus is a P, phosphorus is 15 electrons, how are they arranged around the nucleus? Well, on the second to last page of your notes, there are 3 rules for filling atomic orbitals. Second to last page. That's the last page. Second to last page. No, just turn it over. Okay? 3 rules for filling atomic orbitals. Does everybody see that?
Yeah.
Okay? The first rule is the Aufbau principle. Phosphorus has 15 electrons. Where are those 15 electrons going to be? What orbitals are they going to be in? Well, the first rule of filling these atomic orbitals, the first rule that atoms follow is called the Aufbau principle. A-U-F-B-A-U. A lot of people just call it the golf ball principle, but it's the Aufbau principle. We already learned everything in nature wants to be in the lowest possible energy state. Everything, the ground state, the lowest energy is where we start. So Aufbau principle simply says we start at the bottom and work our way up. We don't go to the next one until this one's completely filled. You start at the bottom, work your way up. That's what the Aufbau. So we're going to start down here at the bottom. Okay? So we put in 1 electron. And I'm putting in an up arrow. The second one is going to be a down arrow. Because only 2 electrons can go into any orbital, and they must have opposite spins. So C, now right there in your rules, is called the Pauli exclusion principle. I already mentioned it, but here's the definition of it. The Pauli exclusion principle. Only 2 electrons can go into any orbital, and they must have opposite spins. That's what the up and the down arrow represent, the opposite spins. Okay? So I go 1, 2. Then I go, so now this lowest energy level, the first energy level is filled. Notice after 2, I'm at the end of the first row in the periodic table. So then I go, the third electron goes into that 2s. Then the fourth electron goes into the 2s, but it's got to have opposite spin. It's going to go down. That's beryllium. That's 4 electrons. Notice beryllium is at the end of that first left side of the goalpost on the periodic table. How many electrons total can be in the S sublevel, and on any S sublevel, how many electrons total can be in it? 2. Notice there's 2 columns on that left side of the goalpost on the periodic table. So now where's 5? Well, it's boron. Notice we make a big jump over to boron. Okay? So that's going to be 5. Now this is where we're going to use our third rule. Our third rule is called Hund's rule. This is B on your notes. B in your notes. Hund's rule. And it says that when you're filling degenerate orbitals, when you're filling orbitals on the same sublevel, you're going to put 1 electron into each before you begin to pair them up. Electrons are negative. They're going to repel one another. You're going to put 1 electron into each before you begin pairing them up. And they all have to have the same spin. They all have to be going up, or they all have to be going down. Now, if you want to eat the crust first, you can be all downs and then come back with ups. But they just all have to have the same spin. 1 into each, same spin. Okay, so that's 7. That's what nitrogen would look like. And then we go start filling up 8, 9, and 10. What element has 10 electrons? Neon. Where is it on the second row? At the very end, right? Noble gases. So the second energy level is completely filled. So the next electron goes onto which energy level? It's into the 3s on the third energy level, right? You're on the third row of the periodic table. Sodium has 11 electrons. And then magnesium has 12 electrons. Now notice again, now that second column of that goalpost is now, we're to the end of that one. So then 13 again, we jump across. Now, how many electrons total can be in the P sublevel? 6. How many how many columns are there over here? 1, 2, 3, 4, 5, 6. How many electrons can be in a D sublevel?
10.
There's 5 orbitals, so you can have how many electrons? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many electrons can be in the F sublevel? There's 7 orbitals, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This periodic table is arranged completely by these electron sublevels. This is your S, electrons are going into the S, electrons are going into the P's, electrons going into the D's, electrons going into the F sublevels. It's amazing how it all works out like that when you put it in an increasing atomic number. So now let's just keep going though, because we got one more curveball to go. And we are out of here at 225. Wonderful. Okay, 225. So, I'm going for 15. 2, 4, 10, 12, 13, 14, 15. So according to Hund's rule, phosphorus is going to have 3 unpaired electrons. It's not going to have a pair and 1 unpaired. It's going to have 3 unpaired electrons. Now, so you guys have to realize that any time you put a magnet on your refrigerator, it's because of these unpaired electrons. All magnetism is the result of these electrons, okay? So let's do, well, I don't want to get iron yet, but if a magnet like iron's going to end up having 4 unpaired electrons. So 50% of them are all going to be going up clockwise. The other 50%, just because of random, are going to be all going down counterclockwise. When you have a magnet, all of the iron atoms that they're up arrows, they're clockwise, are all going one way or at one end, and all the down arrows atoms are all on the other end. And because of those spinning electrons, that's what creates the North Pole and the South Pole. It's what causes a magnet to be magnetic, is these unpaired electrons, half of them going up, half of them going down. North and a South Pole creates magnetism. So the next time you see a magnet on your refrigerator, you can just know, hey, there's little tiny electrons in there spinning, and because half of them are spinning clockwise on one end, the other half are spinning counterclockwise on the other end, that's what's making your magnet stick to the refrigerator. Okay? All magnetism is the result of these electrons. Now you need to be more excited than what I'm seeing in your faces, because that's pretty darn exciting right there. That's interesting. Okay? All right. One more curveball though. Okay? You know how are our electron energy levels evenly spaced? No. As you get farther out, they start getting closer and closer to one another. So there's not as much difference in energy. Unfortunately, when you start getting going from the 4s, from the 3d, the 3rd, and the 4th, remember, we're on energy levels. With the lower energy means the one that's going to be held most tightly, not the distance from the nucleus. So when we're comparing the most probable place based upon the path that the electron's taking in these complex wave patterns, a 4s, n equals 4, L equals 0, that electron's going to be about this. Here's the nucleus over here. It's going to be about this far from the nucleus. A 3d, on average, is going to be about this far from the nucleus. Which makes sense. The 4th energy level is farther away than the 3rd energy level. However, the 4s electron doesn't stay out there all of the time. There's these small but significant amount of times it's closer to the nucleus. What does that mean about its attraction to the nucleus? It's stronger. So even though most of the time it's farther away, it's actually held more tightly than a 3D, which means it's lower energy. The Aufbau principle says that atoms, the electrons are going to go into the lowest energy level first. So, when we're building this, the 4s here is actually going to be lower in energy than the 3D. Okay? 4s is going to come before 3D. So it's actually going to be on any energy level. Anytime you do this, the 4s comes before 3D. So if I want to do iron element number 26, and I'm going to be filling with electrons, okay? I have my 15, 16, 17, 18. Well, the 19th and 20th electrons are going to go into the 4s before they go into 3D. So you get 1, 2. So that's 20. Then we go 1, 2, 3, 4, 5, 6. So iron has 4 unpaired electrons, and so all of the ups get on one end of the magnet, all of the downs get on the other end of the magnet, and that's what makes a iron magnet magnetic. It's the spinning arrows. But the 4s comes before the 3d. Now, unfortunately, the farther out you go, the f's are even less attracted. So there's even more overlap. So when we build this, we continue to build it. You get 4s, 3d. Then, after 3d comes 4p. 1, 2, 3, 4p. Then we get 5s. Then we get 4d. 1, 2, 3, 4, 5. 4d. Okay? But we don't see anything about the f's yet. So you go to 4d, then you 5s, 4p, 5s, 4d, 5p, and then you go to 6s. Then we finally hit 4f. 4f, just above 6s. Then we go to 5d. Then you go to 6p. Then you go to 7s. Then you go to 5f. And then 6d is as high as you need to go, because that's the last known.
Does that make sense?
Okay? Does it make sense? Not really. It's kind of crazy. But that's the way it is. Now, you may have learned that in 8th grade, you say 1s, 2, 2s, 2, 2p, 6, 3s, 2, 3p, 6. What do the 2s and the 6s mean?
Number of electrons.
Total number of electrons in those sublevels. But this is where the first overlap is. 4s2, then 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14. Okay? 5d10, 6p6, 7s2, 5f14, 6d10. That is crazy. But yes, you have to know that.
Can you repeat that?
You have to know it. Okay? Now look, there's 3 ways. I got 3 minutes to tell you the 3 ways to learn that. Good, bad, and ugly. The ugly way is to just try and memorize that. Okay? You're gonna mess up. Okay? You're gonna mess up. I still struggle. I've been doing this forever and ever and ever, but it's just hard to just kind of keep that all straight. But there is a pattern to it, but you still, it's hard. The second way is to use what we call the diagonal rule, which is on the very last page of your notes. Your diagonal rule. Now, what do you think you draw if it's called the diagonal rule? Diagonals. Okay? So when you have this, you draw a diagonal. Now follow me. Follow me. Draw a diagonal. 1s.
There are some blanks on the other page.
Okay, just do it. Follow this. Don't worry about the blanks. 1s. Then we go to 2s. Draw the diagonal this way. 2s. Then you keep drawing diagonals. 2p, 3s. Okay? 3p, 4s. 3d, 4p, 5s. There's your first overlap. 3d, 4p, 5s. Keep just drawing diagonals. It tells you the order in which everything fills, and you can stop at 6d. Okay? That tells you that exact same order. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4F, 5D, 6P, 7S, 5F, 6D. Tells you the exact order to follow. Now, that works, but that's a lot of work. Periodic table is always here for how they follow. This is your S section on the periodic table. Electrons are always going into the S here. Whatever row you're on is the energy level. This is your P section of the periodic table. 6 of them. This is the D section. This is the F section right here. Okay? So we go, now helium technically should fit right there, 1s2. But the reality is it acts like a noble gas, so they put it over here. That's the first energy level filled. Then the third electron, 2s1, 2s2. Now the second energy level is filled. So we go to 2p. 1, 2, 3, 4, 5, 6 electrons in the 2p. Now it's filled. So where do I go after 2p? Well, I go to the third energy level. I'm in the S section, so it's going to be 3s1, 3s2. Well, where do I go after 3s? Well, 12, I go to 13. Well, which section am I in? 3p. 1, 2, 3, 4, 5, 6. Well, 18, where do I go next? I go to 19. What section am I in? 4s. And then for the first time, I go into the center, and the D's are 1 behind and the F's are 2 behind. They fit in here, but we'll start with that on Monday. Okay? They do actually. Well,